The last belt stops moving at 11:47. Thomas Wardell watches the main drive wheel complete its final rotation, the leather belt slackening as the steam pressure bleeds away 3 floors below. The wheel, 12 feet across, cast in 1867, settles into stillness with a sound like a man taking his last breath. He's the night foreman. This is his ritual. The gear hall stretches 60 feet before him, a cathedral of cast iron and shadow. The overhead lamps have been extinguished for 20 minutes now. Only his lantern remains, throwing amber light across the massive reduction train that steps power down from the drive wheel to the factory's eastern wing. 5 gears, each one larger than a millstone, teeth as long as a man's hand. They should be completely still. Wardell lifts his lantern higher. The light catches on oil film coating the gear teeth, that rainbow sheen of good lubrication. He's about to turn away when he hears it. Click. Not loud, a sound like a pebble dropped on slate, but distinct, resonant, coming from somewhere deep in the gear train. He freezes. The factory is never truly silent. Steam pipes tick as they cool, floorboards settle, metal contracts in the November air. But this sound is different, purposeful, mechanical. Wardell approaches the train slowly, boots echoing on the wooden planking. The gears tower above him, their teeth interlocking in precise geometries that took Prussian engineers 3 months to align. He places his palm against the frame of the largest gear, the bull gear, they call it, 8 feet in diameter. Cold iron, completely still. He waits, counts to 60 in his head, breathing shallow. Nothing. Then click. Closer now, definitely coming from inside the gear mesh. He leans in, lantern extended, studying the point where the bull gear's teeth engage with the secondary pinion. In the shifting light, he thinks he sees something. A reflection displaced, a highlight that wasn't there before. But that's impossible. The entire train is disengaged. The clutch assembly was thrown 2 hours ago. The drive shaft from the steam engine sits motionless, separated by a full 3 inches of air gap. Nothing connects these gears to any source of power. Wardell touches the bull gear's rim. His fingertips come away black with oil and graphite dust. In the lantern light, he notices something odd, a thin line in the dust coating, perfectly straight, running along the top of one tooth, as if something had shifted, recently. Click. He jerks his hand back. The sound came from directly beneath his palm. For a long moment, Wardell stands there in the vast darkness, lantern held high, watching 5 tons of idle gearing. His pulse drums in his ears. Cold air moves through the hall, carrying the smell of machine oil and coal smoke. He knows metal, knows machinery, has worked in mills since he was 14 years old. And he knows with absolute certainty that something just moved. The day shift arrives at 6. Samuel Price is first into the gear hall, carrying his leather tool satchel and a tin of breakfast. He's one of the senior machinists, 42 years old, trained in Manchester, with hands that can detect a 1,000th inch misalignment by touch alone. He notices it immediately. The bull gear's index mark, a small brass tag riveted to the rim, has moved. Not much, perhaps a 1/4 inch. But Price marked its position himself yesterday afternoon, aligning it with a chalk line on the stone floor below, part of the routine inspection protocol. The brass tag now sits 3 gear teeth past the chalk line. Price sets down his satchel slowly, crouches beside the gear. In the dust coating the floor, he can see scratch marks, faint concentric arcs where the gear's lower edge has dragged through grit and metal filings. Oi, Wardell. The night foreman is still here, sitting on a tool bench near the western wall, nursing a tin cup of tea. He looks like he hasn't slept. You see it? Wardell asks. The bull gears rotated. Price keeps his voice level, professional. Maybe 3 inches on the rim. You run anything last night after shutdown. Nothing ran. Full stop at 11:47. Wardell stands, walks over. I heard it moving after midnight. Just clicks, little movements. Price looks at him. They've worked together 8 years. Wardell isn't given to imagination. Show me. They inspect the gear train methodically. First, the clutch assembly, completely disengaged, the gap between driving and driven shafts measuring exactly 3 1/8 inches. No contact, no possibility of residual connection. Then the reduction gears themselves, each one mounted on massive cast-iron bearings, each bearing housing bolted directly to the stone floor. No play in the system, no loose mountings. The teeth are perfect. Prussian cutting, every surface true to within 0.02 of an inch. The kind of precision that costs a factory owner 6 months of profit. But as they examine the mesh points, where teeth engage, Price notices something strange. He pulls a magnifying lens from his satchel, leans close to where the bull gear's teeth meet the secondary pinion. There's fresh oil displacement here, he says quietly. You can see it. The film's been disturbed. The oil coating every gear tooth shows tiny stress patterns, microscopic waves in the lubricant where metal has pressed against metal. Recently, within hours. That's not from yesterday's running, Price adds. This is new contact. They hear footsteps, more workers arriving. The morning light strengthens through the eastern windows, illuminating the gear hall in cold grey tones. Wardell touches the bull gear again. This time he leaves his palm there, fingers spread across the rim. Wait, he says. They wait. 30 seconds, 60. The factory comes alive around them. Boilers heating, distant machinery starting, voices echoing from other halls. Then Wardell feels it. Not sound, not visible movement, just the faintest sensation of strain in the metal, a pressure building, like the gear is breathing. Price sees his expression. What? Put your hand here. Price places his palm beside Wardell's. They stand there together, 2 men touching 5 tons of supposedly motionless iron. And they both feel it, a vibration so subtle it's almost imagined, a frequency just below hearing, transmitted through the gear teeth, through the massive frame, through the stone floor itself. Something is moving. But nothing should be. By 2 o'clock, the phenomenon has become undeniable. The bull gear has rotated another half-inch. The movement is visible now to anyone who cares to look. The brass index tag has traveled past 2 more chalk marks on the floor. 7 men stand watching, machinists and fitters, some of the most experienced hands in the factory. No one can explain it. Check the mains again, says Robert Halloway, the works engineer. He's a methodical man, educated at technical college, skeptical of anything that can't be measured with instruments. 2 machinists climb the access ladder to the upper shaft gallery. They verify, for the 3rd time, that the main drive shaft sits completely isolated. The clutch remains thrown. The steam engine in the basement continues running, powering the factory's other departments, but no mechanical connection exists to this gear train. Yet the gears continue their slow, intermittent rotation. Price has been timing it. Every 11 to 14 minutes, a small movement, always forward, never backward. Sometimes just a click, a single tooth advancing through its mesh. Sometimes a longer creep, lasting 3 or 4 seconds, the gear rim sliding forward perhaps a 1/4 inch before stopping again. He's placed his machinist's calipers against the gear teeth now, watching for any movement. The tool rests in contact with the steel, its measuring faces spread precisely across 2 tooth surfaces. The other men gather around, waiting. The gear hall has taken on an odd quality. Despite the factory's normal operation, looms clattering in adjacent buildings, steam hammers pounding in the forge, this space feels separate, isolated. The massive gears stand like monuments in the filtered afternoon light, their shadows sharp against the stone walls. There, someone whispers. The caliper shifts, visibly, definitely. The measurement faces slide along the tooth surface as the gear creeps forward. 1 millimeter, 2, 3. Then it stops. Price doesn't move the caliper. His hands remain perfectly steady, holding the instrument in place, but his breathing has changed. Faster, shallower. Did anyone else feel that? Asks a younger machinist named Dobbs. Feel what? The floor just now, when it moved. They all go still, listening, feeling. The wooden planking beneath them, 3-inch oak boards laid over stone, carries vibrations from across the factory. The regular thump of the steam engine, the high-frequency buzz of cotton spindles, the rhythmic crash of power looms. But Dobbs is right. There's something else. A low-frequency pulse, barely perceptible. It comes in waves, seemingly synchronized with the gear train's movements. Holloway kneels, presses his palm flat against the floorboards. He's a large man, heavy, with hands that have lifted steel castings and turned bronze valve bodies. But right now his expression is uncertain. It's coming through the foundation, he says. Some kind of resonance. From where? Wardell asks. I don't know. They trace the vibration by touch, moving across the gear hall like men searching for a faint draft. The sensation grows stronger near the western wall, where the main bearing pedestals bolt into the stone floor. Weaker toward the east, away from the basement levels. Price places his ear directly against the bull gear's iron frame. Through the metal, he hears something that makes his skin prickle. A deep harmonic, not quite sound, more like the memory of sound, resonating at the edge of perception. It pulses, rises, falls, continues. The whole building's vibrating, he says, pulling back. Everything, the foundations, the walls, it's all singing. Holloway looks at him sharply. That's not helpful, Samuel. I'm telling you what I hear. The gear creeps forward again. This time they all see it clearly. The teeth sliding through their mesh, the oil films stretching and breaking, the massive wheel rotating perhaps 3 degrees before stopping with a distinct thunk that reverberates through the floor. Something falls from the overhead beams, a small cascade of rust particles, dislodged by the vibration, drifting down through the afternoon light. No one speaks. The gear train stands before them, 5 wheels of progressively larger diameter, each one precisely cut, perfectly balanced, engineered to transmit thousands of horsepower during operation. But now, disengaged and idle, they move without power, without explanation. And somewhere in the building's bones, that low-frequency hum continues its patient, rhythmic pulse. Holloway organizes a systematic investigation. By 7 o'clock, the gear hall has been cleared of all non-essential personnel. 6 men remain: Holloway, Wardell, Price, 2 senior fitters named Cobb and Mendel, and a young technical apprentice tasked with recording observations in a leather-bound logbook. They begin with first principles. Every mechanical movement requires a force, Holloway states, pacing before the gear train. No exceptions. Something is driving this system. We find the source, we solve the problem. They check each potential energy input. The main drive shaft, completely disengaged. They insert wooden blocks into the clutch gap to prove no contact exists. The shaft from the steam engine continues rotating in the basement, but 3 inches of air separate it from the gear train. Secondary power takeoffs. The factory has multiple belt drives running throughout the building. Each one is traced and verified. None connect to this system. Overhead line shafts. 2 parallel shafts run the length of the gear hall, suspended 20 feet up, carrying power to auxiliary machines. Both have been stopped. Their bearings confirmed motionless. Direct manual interference. The gears are inspected for any sign of deliberate manipulation. No ropes, no levers, no hidden connections. Every potential cause is eliminated. Yet the gear continues its intermittent rotation. Cobb, the older fitter, a man who's worked with steam machinery since before Halloway was born, suggests checking the bearing assemblies. Could be something binding and releasing, he says. Old seizure patterns. Rust. They disassemble the bull gear's main bearing. It's a massive bronze assembly, 12 inches in diameter, sitting in a cast-iron housing filled with wool waste and tallow lubricant. The bearing surfaces gleam in the lantern light. No rust, no scoring, no sign of binding. These bearings are perfect, Price says, running his fingers across the bronze. Better than perfect. They're broken in, smooth as glass. They reassemble everything. The bearing slides back into place with the well-fitted ease of quality engineering. The gear creeps forward twice during the bearing inspection. Both times, the men are touching various parts of the assembly. Both times, they feel the movement transmit through the metal, a slow, deliberate pressure, like something vast pushing from within. Mendel suggests a radical test. Disconnect the entire train, take out the coupling pins, separate every gear. Halloway considers this. It would mean hours of work, but it would prove whether the movement originates in the bull gear itself or transmits through the mesh from elsewhere in the system. Do it, he says. They begin disconnecting the reduction train, working by lamplight. Each gear rides on its own shaft, connected to the next through precisely machined coupling pins. Remove the pins, and each wheel becomes completely isolated. The work is careful, deliberate. These are precision mechanisms, not to be handled roughly. By 9 o'clock, the train is fully separated. 5 independent gears, each on its own bearing assembly, with no mechanical connection between them. The men step back, wait. 11 minutes pass. Then the bull gear moves, not much, just a fraction of an inch, but unmistakable. And here's what makes Price's hands go cold. 3 seconds later, the secondary pinion, now completely disconnected, sitting 6 inches away from the bull gear, also moves. In the same direction, the same small rotation. Then the third gear, then the fourth. A wave of motion, passing through disconnected machinery. That's not possible, Halloway says quietly. But they all saw it. The gears moving in sequence, like a memory of their former connection, even though no mechanical link remains. Wardell walks to the western wall, where the bearing pedestals mount to the foundation. He kneels, pressing his ear against the stone floor. Listen, he says. One by one, the others join him. 6 men lying on their sides on the gear hall floor, ears pressed to cold stone. Through the foundation, they hear it clearly now. A deep, resonant vibration. It comes in pulses, rising and falling with mechanical regularity, not from the gear train, from somewhere below, somewhere vast. The building itself is transmitting energy, through its bones, through cast iron and dressed stone and oak beams, a harmonic frequency that finds every piece of heavy machinery and sets it trembling. The gears aren't being driven. They're responding. Dawn finds them still working. Price has spent the night mapping the vibration patterns. Using chalk and careful measurement, he's marked every point where the floor transmits the strongest pulses. The pattern that emerges is not random. Look, he tells Halloway, showing him the chalk marks scattered across the gear hall floor. It's not uniform. The vibration is directional, strongest here near the western wall, weaker toward the east, and it pulses at exactly 42 cycles per minute. 42, Halloway repeats, his eyes narrow. The main engine runs at 84 revolutions per minute. Half speed, Price says, harmonic. They descend to the basement levels, following the vibration to its source. 3 floors down, in the engine room, the great steam engine continues its patient work. A walking beam design, installed in 1863, with a flywheel 16 feet in diameter and weighing 11 tons. The engine drives the factory through a complex arrangement of shafts and belts, but most of its power goes to a single massive shaft, the main drive, that runs the length of the building at basement level. Holloway studies the main drive shaft. It's 8 inches in diameter, forged steel, perfectly balanced. It spins at a steady 84 revolutions per minute, carrying power to various departments. But the shaft doesn't run alone. Mounted along its length are multiple flywheel assemblies, heavy iron wheels that store energy and smooth out the engine's power delivery. 8 flywheels in total, each one weighing between 2 and 4 tons. When was the last time these were inspected? Holloway asks the engine room supervisor. The flywheels, been years. They don't need much maintenance, just lubrication. Holloway approaches the nearest flywheel, places his hand on its rim as it rotates. Through the metal, he feels something odd, a secondary vibration, a wobble so subtle it's barely there. "Stop the engine," he says. "Stop sir, that's the main power. We'd have to shut down half the factory." "Then shut it down. I need to see this shaft at rest." 20 minutes later, with looms idle and workers standing confused in silent workshops, the great steam engine comes to a halt. The walking beam completes its final stroke. The flywheel coasts, slowing gradually, its momentum bleeding away through bearing friction. The main drive shaft, spinning at 84 revolutions per minute moments ago, begins to slow. And here's what Holloway observes. The shaft doesn't stop cleanly. It creeps, advances in small increments as the various flywheels along its length release their stored energy at slightly different rates. Each flywheel, mounted at different points, with slightly different moments of inertia, continues trying to turn the shaft even as friction brings the system to rest. The result is a slow, pulsing rotation. The shaft advances, stops, advances again, like a ratchet mechanism clicking forward in tiny increments. 42 pulses per minute. Each pulse transmits through the shaft bearings, into the cast iron bearing pedestals, through the foundation, up through the building's stone floors to every piece of machinery bolted to the structure, including the gear train 3 floors above. "Mother of God," Holloway says softly. They return to the gear hall. Price is waiting, holding a stopwatch and a notebook filled with precise timings. "The bull gear moves every 13.7 seconds, Price reports. "I've timed it 68 times now, consistent to within 1 second. 42 times per hour, Holloway says. "No, wait, 44, arithmetic. 43.8 movements per hour, Price corrects, based on 13.7-second intervals, almost exactly the pulse rate you found in the main drive." They stand together, looking at the massive gear train. Understanding begins to dawn. "But the clutch is disengaged," Wardell says. "The drive shaft isn't connected." "It doesn't need to be," Holloway replies. "The vibration is coming through the foundation. Every time the main drive pulses, it shakes the building, just slightly. And the gear train, 5 tons of precision machinery, perfectly balanced, sitting on bearings so smooth they're nearly frictionless, responds to that shake." Price shakes his head. "That can't be enough force. We're talking about vibrations transmitted through stone and cast iron, dissipated across hundreds of feet. The energy reaching this gear train must be minuscule." "It is minuscule," Holloway agrees. "But look at the system. Really look at it." He walks to the bull gear, runs his hand along its rim. "This gear rotated at full speed for 10 hours yesterday, transmitting 70 horsepower, building up heat, building up stress in the metal. The teeth were pressed together under load, the bearings were hot, the shaft was slightly twisted by torque." He traces the gear's circumference with one finger. "Then we stopped everything, threw the clutch, cut the pow, but all that energy didn't just vanish. The metal contracted as it cooled. The shaft tried to unwind its stored torque. The gear teeth, pressed together for hours, slowly relaxed their contact." "Residual energy," Price says quietly. "Exactly. The gear train is like a wound spring, storing tiny amounts of strain energy from yesterday's operation. And every time the building vibrates, every time that pulse comes through the foundation, it shakes loose a little more. The backlash between gear teeth allows microscopic movements. The bearings, so perfectly smooth, offer almost no resistance, and the gear creeps forward bit by bit, releasing stored energy that accumulated during the day's work. Wardell looks skeptical. You're saying the gears remember being in motion? No, I'm saying the metal remembers being under stress, and it's slowly returning to equilibrium. They examine the gear teeth again, this time looking for evidence of thermal changes. Price produces a metallurgist's temperature chalk, special compounds that leave visible marks at specific temperatures. He marks several gear teeth, noting their current temperature. Over the next hour, they monitor the chalk marks. Sure enough, they detect subtle temperature variations. The gear teeth that were in contact during yesterday's power transmission are still fractionally warmer than those that were idle. The difference is measured in fractions of a degree, but it's there. Thermal drift, Halloway says. The whole assembly is still cooling from yesterday, contracting, and that contraction is biased in the direction of rotation because that's where the stress was applied. They find more clues. The oil film on the gear teeth shows patterns consistent with repeated light contact, the kind that happens when surfaces touch and separate thousands of times rather than remaining in continuous mesh. The bearing journals show microscopic wear patterns that form concentric rings, evidence of tiny oscillating movements rather than steady rotation. Everything points to the same conclusion. The gear train isn't being driven by any external force. It's releasing energy it stored during operation. And the building's vibration, transmitted through the foundation from the main drive shaft's uneven deceleration, provides just enough stimulus to overcome static friction and allow those tiny, creeping movements. The mystery has a solution. But that solution opens new questions. How long will this continue? What happens when similar residual forces exist in larger machines, in systems with more stored energy? Price voices what they're all thinking. If this gear train can move on its own for 12 hours after stopping, what about the big machinery, the trip hammers, the rolling mills? No one answers, because no one knows. A week later, the factory brings in consulting engineers from Manchester. They arrive with instruments, precision micrometers, vibration detectors, temperature sensors, even a portable seismograph designed for measuring ground tremors near mining operations. The gear hall becomes a laboratory. Lead engineer is a man named Patterson, 45 years old, educated at Cambridge, with 15 years of experience in heavy machinery analysis. He approaches the problem with academic thoroughness. First, we establish baseline measurements, he announces, directing his team to map every aspect of the gear train's geometry, temperature distribution, and vibrational response. They work for 3 days straight. The measurements reveal details the factory's own machinists never suspected. The bull gear, for instance, is not perfectly circular. It deviates from true round by 6/1000ths of an inch, invisible to the eye, barely detectable with standard tools, but enough to create an imbalance that stores energy when the gear rotates under load. The bearing assemblies, while superbly manufactured, have microscopic imperfections. Each bearing's rolling elements, the bronze surfaces that support the gear shafts, have tiny variations in hardness. These variations create pressure points. Under load, these points compress slightly, storing elastic energy like miniature springs. Even the gear teeth themselves have microscopic texture. Examined under magnification, each tooth face shows a landscape of tiny ridges and valleys, invisible to casual inspection, but crucial to how the surfaces interact under pressure. Patterson explains his findings to the factory management and assembled workers. What you're witnessing, he says, is a phenomenon we might call mechanical memory. These gears don't remember motion in any conscious sense, but the metal, the physical structure, retains patterns of stress from previous operation. He uses a blackboard to sketch diagrams, arrows showing force directions, equations describing thermal expansion and contraction, mathematical representations of harmonic coupling. Consider the complete system, Patterson continues. Yesterday, this gear train operated for 10 hours, transmitting 70 horsepower. That's 520,000 foot-pounds of work. Most of that energy went into useful work, driving machinery. But a small fraction, perhaps 1/10 of 1%, was stored in the system itself, as heat, as elastic deformation, as microscopic compression of metal crystals. He taps the blackboard with his chalk. When you stopped the machine, that stored energy didn't disappear. It began releasing slowly over hours. The metal cooled. The compressed areas expanded back to normal dimensions. The gear teeth, pressed together under load, gradually relaxed their contact. But that doesn't explain the continued movement, Holloway interjects. We've now observed this phenomenon for 7 days. Surely any stored energy would have dissipated in that time. Patterson nods. You're correct. Simple thermal cooling would finish in a few hours. What we're seeing is more complex. It's a cascade effect involving multiple mechanisms working together. He lists them. First, residual torque in the heavy gear shafts. Steel shafts 8 inches in diameter, twisted by thousands of foot-pounds of force, don't simply spring back instantly when load is removed. The metal's crystalline structure takes hours to fully relax. Second, thermal drift throughout the system. Different metals, steel gears, bronze bearings, cast iron frames, expand and contract at different rates as temperature changes. This creates internal stresses that resolve themselves through tiny movements. Third, harmonic coupling from the main drive shaft. Even when clutch disengaged, the gear train sits in a building that vibrates at specific frequencies. These vibrations, transmitted through the foundation, provide periodic stimulus that overcomes static friction. Fourth, backlash oscillation between gear teeth. Every gear mesh has designed clearance, microscopic gaps that prevent binding. Under vibration, teeth rock back and forth within this clearance, gradually working toward equilibrium positions. Fifth, frictional stiction and release cycles in the bearings. Lubricant film breaks and reforms as loads change. Each break and reform cycle allows infinitesimal rotation before friction reasserts itself. Sixth, structural resonance through cast iron frames. The massive gear frames act as tuning forks, responding to building vibrations at specific frequencies. This resonance amplifies certain movements while damping others. And finally, flywheel inertia stored in auxiliary shafts throughout the factory. Multiple rotating masses, all gradually decelerating at different rates, creating a complex pattern of vibrations that persist for days after main power is cut. Each mechanism alone is trivial, Patterson concludes, but together, interacting, they create sustained motion. The gear train isn't moving because of any single force. It's moving because it sits at the intersection of multiple subtle influences, each one reinforcing the others. He pauses, looking at the assembled workers. In essence, gentlemen, your machinery is so well made, so precisely balanced, and so carefully integrated into the building's structure that it responds to forces we normally consider negligible. You've built a machine sensitive enough to detect vibrations from machinery hundreds of feet away, and to respond to temperature changes measured in fractions of a degree. Someone asks the practical question, is it dangerous? Patterson considers carefully. No, the forces involved are minuscule. The gear train will eventually come to complete rest, probably within another week. What you're seeing is simply mechanical systems seeking equilibrium. It's unusual only because your machinery is unusually well made. In most factories, friction and misalignment would prevent these subtle effects from manifesting. But Price has a different question. Could this happen in other machines, larger ones? Patterson's expression grows serious. Yes, in fact, it probably does happen. Constantly. We simply don't notice because most machinery never sits idle long enough for us to observe it, and most machines are not as precisely balanced as this gear train. He gestures toward the massive gears. What you've discovered here is that heavy machinery doesn't simply stop and start. It exists in a state of continuous dynamic equilibrium, responding to forces too subtle for casual observation. Every shaft, every gear, every bearing is constantly adjusting, releasing stored energy, absorbing new vibrations, seeking balance. The machines, he adds quietly, are always moving. We just don't usually watch them closely enough to see it. There's a lesson there, perhaps. Build something well enough, with tolerances tight enough, with materials strong enough, and with geometry true enough, and it will begin to reveal the world around it. Not through words, but through motion, through the subtle language of force and response. The old machinists understood this intuitively, even if they lacked the mathematics. They knew that a machine could speak if you listened, a bearing that warmed too quickly, a shaft that rang with the wrong tone when struck, a gear that shifted its resting point by half a tooth between dusk and dawn. These were not mysteries in the supernatural sense. They were messages from the physical world, carried through iron and oil and air. To them, the gear train's midnight motion was not an omen. It was a reminder that every machine is part of something larger, a web of stresses, temperatures, vibrations, alignments, misalignments, and forces seen and unseen. A reminder that in the industrial age, no mechanism truly stood alone. Every bolt, every casting, every shaft was connected to the factory floor, to the river outside, to the weather overhead, and to the labor of the men who kept it alive. And as long as those connections existed, as long as energy moved through the world, even a silent, disconnected gear train could find reason to move. It did not defy physics. It demonstrated them.